Okay, so any questions on trace distance? Okay, so today we will continue discussing trace distance, and then hopefully we'll have some time to start discussion on fidelity, how to extend the classical fidelity definition to quantum mechanics. Okay, so let me quickly recap what we discussed last time. So we studied two classical distances, classical measures of distance between probability distributions. And number one was the L1 distance, या इसका दूसरा नाम है Kolmogorov, but we called it trace distance because that's the name that's used in quantum physics. And if we have two distributions on the same index set x, and we discussed even if the initially the index is not the same, we can easily make the index same. So they have same index, and the classical trace distance was defined as half px qx. Essentially, you take the difference of probabilities at the same index from the two distribution and take its modulus and just add it all up. And if you recall, this was also defined as maximization over a set S such that the probability of an event happening, we don't even actually need the absolute sign. From that set, the difference is maximized. And then we studied the classical fidelity. Fidelity as f px qx, which was essentially the dot product between two vectors such that one vector is px square root, the other vector is qx square root. Whereas the individual values of the probabilities at the index are the components of the vector. Okay, and we didn't show it for classical distance. Today, we will show it for the quantum generalization of this, that this indeed is a metric, which means that it satisfies the triangular inequality. Fidelity is actually not a metric. It doesn't satisfy the triangular inequality, but we can associate something else with the fidelity that can satisfy the triangular inequality. Okay, and that is just the sort of an angle between these two vectors. For example, if you imagine this px square root as one vector and qx square root as one vector, then fidelity is the dot product between the two. So we can define an angle alpha, which can be computed from this fidelity like this, that cosine of alpha is, this fidelity. Since these are already sort of normalized unit vectors, okay, px or qx ka jo sum hai, we already know that it has to add to 1. I don't need px qs magnitude over here. So just cosine of alpha is equal to fidelity. So alpha is cosine inverse of fidelity. तो अगर आप fidelity की वजह alpha से deal करें, then alpha does satisfy the triangular inequality. Triangular inequality यही है कि the distance between 2 points is always smaller than or equal to the, let me draw it here. So in 2 points के दरमियान में जो distance है, let's call it DAB, it's always less than or equal to DAC, where C is any other point. Okay, this already satisfies, and this alpha also then satisfies. That if you take another vector, let's say PQ RX, then the angle between these two vectors is always smaller than or equal to the sum of the other two angles. Okay, so last time we studied a generalized definition for L1 distance to what we call quantum trace distance. And let's say we have two general state rho and sigma. And when I say general, it means that these are mixed states in general. And pure state is just a special case of the mixed state. So this was defined as half trace of rho minus sigma, where the modulus of an operator A is the positive square root of this product A dagger A. And we also saw that we can equivalently define this as a maximization over some projector P such that this D is equal to trace of P rho minus sigma. So essentially, this distance is the maximum difference if you project your state sigma and rho with the same projector and take the trace, then that would be, so you can write it like this as well. Max P trace of P sigma rho P sigma, max P trace of P sigma minus trace of P sigma. So this, if you recall, if this P is a measurement operator, which it can be, because this is a projection operator. So a projective measurement is a projection operator. So this is some measurement outcome. This is some measurement outcome. So basically, you measure something from both states rho and sigma and take the difference. And the trace distance is the maximum such difference over all possible measurements. Okay. So this was the summary of from last time. By the way, आज जो है वो unfortunately we won't be able to have two classes at 4 and 6 क्योंकि 6 o'clock पे Dr. Atta का seminar है. So what we will do, will continue a bit longer. So we'll then leave before the seminar. थोड़ा सा gap होगा, थोड़ा rest कर लेंगे. Okay. All right. So any questions so far? अच्छा, दो प्रॉपर्टीज और जो है वो मैं बल्कि एक प्रॉपर्टी हमने देखी थी ट्रेस डिस्टेंस की, वो ये थी कि इफ यू परफॉर्म अ यूनिटरी ऑपरेशन ऑन the same unitary operation on the two state rho and sigma, it doesn't change the trace distance. And we were able to see it visually from the trace distance that we computed between two qubit states. Okay? Because then unitary operation just the rotation on the qubit state, or चूंकि rotation से distance उनमें change नहीं होता, we saw that the trace distance between two qubit state is half of the geometric distance between the tips of the position vectors of those two states. But we do know already from an example that you did in the quiz, if you pass your states through, let's say, a depolarizing channel, which is not a unitary operation, then the distance change. And in that example, you actually saw that the distance reduces. And I told you that it can be shown in general that any trace preserving channel will basically reduce the distance between the states. So आज आपका जो quiz होगा, you will prove it in general as a theorem, but I'll prove another theorem. After that, I'll give a chance to you. All right. आज जो है वो मैं जो ये प्रोजेक्टिव मेजरमेंट वाला थ्योरम है इसको थोड़ा सा जनरलाइज करूंगा. And the next theorem that we want to prove, and this actually have a very nice interpretation as well, is this, that let EM be a POVM. And by the way, normally physicists जो हैं वो they hate proofs. लेकिन मैं कुछ एक आध इसलिए कर रहा हूँ कि you get into this habit, क्योंकि जो quantum computation and information है, it's essentially a field that is at the intersection of computer science and physics and mathematics. And pure mathematician and computer scientists, they are essentially all about proofs. So almost everything that they say, they try to prove it as a theorem. So क्योंकि जो literature है, you will see it's sort of a mixed literature coming from computer scientists, pure mathematicians, and physicists. So, and you actually can tell by looking at a book if it is written by a physicist or a computer scientist. वो बेशक quantum computation information की. जैसे Nelson and Chuang को देखें तो it has that style के everything is almost like in terms of theorems. तो अगर आप ने कोई और quantum computation पे कोई physicist की book देखी है, तो it's like that other books के जिसमें you sort of go developing things, and you know, there are exercises and so on. So hopefully, you know, you are not put off by, you know, few theorems. Okay, so this is a POVM. So POVM, if you recall, has only this thing, that sum of all these measurement operators is identity. That's the only requirement. And the probability of measurements are given by this. So suppose we have a generalized POVM measurements, and PM is the measurement probabilities for rho, and let's say QM are the measurement probabilities for sigma. Then the theorem says that the trace distance is maximization over this set S such that the trace distance is equal to the classical trace distance between two probability distributions that would be generated by this POVM measurements. ठीक है, कोई आपके पास स्टेट रो है, सिग्मा है, आप किसी भी बेसिस में मेजर उसको करते हैं, प्रोजेक्टिव मेजरमेंट कर लें या जनरलाइज POVM measurement. So at the end what you will get a probability distribution, right? That there is some probability of getting state 1, 2, 3, and so on. So let's call this probability distribution PM. So similarly, you'll get a probability distribution for state sigma. So the theorem says that the trace distance is an upper bound for the classical trace distance between the probability distributions generated by an arbitrary POVM, and the upper bound is equal to this, and this is equal to this for a certain, you know, POVM. Okay, अब देखें कोई भी स्टेट है, लेट्स से आप क्यूबिटिक स्टेट ले लें, जीरो स्टेट ले लें, प्लस स्टेट ले लें, ज़रा आप you have a choice of measuring. Suppose आप उसको 0-1 basis में measure करते हैं, या आप उसको plus minus basis में measure करते हैं, कोई भी, या the basis doesn't even have to be, you know, orthogonal, as long as it satisfy this criteria. तो theorem ये कहता है कि आप दोनों जो states हैं उनके लिए कोई एक basis, एक measurement basis choose कर लें, या एक measurement set choose कर लें, and then you perform measurement. और जो दोनों की probability distribution है उनका trace distance find करें, you will get something that is always going to be smaller than the actual trace distance. But for some, you know, EM, this will be equal to that. So the trace distance is essentially an upper bound for the classical trace distance between the probability distributions. Okay, which essentially means अगर आप इसको रिवर्स में देखें तो अगर दो स्टेट्स जो हैं they are close in quantum trace distance, then their classical measurement probability distributions will also always be close. Okay, because this is always smaller than this one. अगर आप ये max हटा दें, then you can put this sign. Get it? So that's why this is a useful thing. कि आप जो है वो अगर इसको compute कर लेते हैं तो that is essentially the upper bound for your measurement statistics, the difference between the measurement statistics of two states. इसका proof जो है, it's quite easy. It just follows that theorem और जो कुछ हमने अलजेब्रा जो है वो डेवलप किया and follow it closely क्योंकि आप similar जो method है उससे क्विज वाला जो प्रॉब्लम वो भी सॉल्व कर सकेंगे. Okay, so let's start from the definition for the classical distance, which is half this. Now this I know that I can write as ये PM की जगह पे I can write this और QM की जगह पे ये लिख सकते हैं और चूंकि trace linear है I can take trace out और जो even EM है I can even take EM out, so I will get rho minus sigma. Okay, ये put करके तो EM common ले लिया. अब I know that rho minus, अच्छा sorry इसमें modulus भी है. This is now this is equal to half trace of EM into Q minus S, and this is coming from the fact कि अगर आप last lecture से if you remember we argued that we can write rho minus sigma as Q minus S, where Q and S are both positive operators but they are on orthogonal support, which means that they're अगर आप इनके आइगन वेक्टर्स इसके और इसके फाइंड करें तो इसके हर आइगन वेक्टर का इसके हर आइगन वेक्टर के साथ जो प्रोडक्ट है वो 0 है. Okay, so we can write this, but this would be smaller than or equal to half some trace EM Q plus S. उसकी वजह ये है कि यहाँ पे देखें we have a positive operator and then another positive operator and उसकी जो eigen values हैं उनका difference लिया है. So this thing is always going to be smaller than this thing even after taking this modulus. क्यों? क्योंकि ये जो difference है उसकी वजह से क्योंकि ये भी positive number है, so difference is always going to be smaller than the sum. And I don't need anything over here because these are positive operator. So in measurement will also generate positive numbers. So the modulus is not needed anymore. But now I can write it like this. And if you remember, this was shown to be equal to rho minus S mod. And now I can take this sum inside the trace because trace is linear. But this is identity because this is a POV measurement. So this is half trace rho minus sigma, which is equal to D of rho minus sigma. And so we can see that this D PMQM is less than like this. Okay, any question about the proof? ये वाला यहाँ पे, हाँ, क्योंकि ये पॉजिटिव नंबर है ना, ये भी पॉजिटिव ऑपरेटर है, ये भी पॉजिटिव ऑपरेटर है, इनकी आइगन वैल्यूज भी पॉजिटिव है, ठीक है। सो इसका मतलब है इनका सम भी पॉजिटिव होगा। सो आप मॉड पुट करें ना करें, इट्स द सेम थिंग। ओके जी। हम्म हम्म। ये इसमें और ये नहीं, ये मॉडुलस है और यहाँ पे मॉडुलस जो है वो बाहर है, सो दे आर नॉट द सेम, ठीक है। एंड दिस रो माइनस सिग्मा जो है, ये टोटल पॉजिटिव ऑपरेटर नहीं है। रो भी पॉजिटिव है, सिग्मा भी पॉजिटिव है, लेकिन इनका जो डिफरेंस है इट माइट नॉट बी अ पॉजिटिव ऑपरेटर, ठीक है। हाँ, दो रो माइनस सिग्मा, अब ये पॉजिटिव ऑपरेटर क्योंकि ये बाहर मॉडुलस है ना। ओके, so let's see if getting comfortable with this thing or not. So suppose I have a channel which has this property that it is trace preserving. So the question is, can you show that in general then the trace distance hai, after the state rho and sigma pass through this channel, the distance is smaller or equal to the distance before they pass through the channel. प्रॉब्लम की समझ आ गई, क्या करना है? ट्रेस प्रिजर्विंग का मतलब समझते हैं ना, कि सिग्मा इसे पास करके तो ये रो ऑफ सिग्मा बना है, बट ट्रेस ऑफ सिग्मा इज इक्वल टू ट्रेस ऑफ, सिमिलरली फॉर रो। चैनल के लिए किया था आपने। हाँ, अब ये तो आपने थ्योरम प्रूव करना है ना, वो तो। हाँ, लेकिन उसमें तो हमें पता था ना कि वो उस तरह का, तो ये तो एक जनरल चैनल है, वी डोंट नो व्हाट्स द फॉर्म। तो इसका जो प्रूफ का तरीका है वो एसेंशियली जो ये थ्योरम है ना, कि यू कैन राइट द डी एज सम प्रोजेक्टर टाइम रो माइनस सिग्मा, so this is a good starting point for this. Okay, so basically you can start from this और इसको some projector time difference लिख के and then start manipulating it, and use this property, and you also will probably need somewhere this thing, somewhere that, and then this trace preservation, and see if you can show that this is smaller than that. हाँ हाँ, कल के लेक्चर नोट की समरी इधर ही है कहीं, ये इसके पीछे है, ये समरी। सॉरी, ये अब प्रॉब्लम उसके पीछे चला गया। आप आपस में डिस्कस कर सकते हैं वैसे। कर लिया आपने? आपने सोचा अकेले बैठने का फायदा नहीं है? हैं?
ट्रेस डिस्टेंस सरफेस को इन टर्म्स ऑफ मैक्सिमम में भी लिख के फिर देन हम लोग फॉरवर्ड कर सकते हैं ना,
हाँ।
प्रॉब्लम।
हाँ, शुरू यहाँ से करें। अब इसमें आप देखें कि जैसे रो माइनस सिग्मा है, इसको आप किसी से रिप्लेस कर सकते हैं। क्या आपने अल्टीमेटली इसको कन्वर्ट करना है? ये आपने रो माइनस सिग्मा कैसे लिख लिया? ये तो ई ऑफ रो और ई ऑफ सिग्मा नहीं आना चाहिए। हाँ, हाँ। तो अल्टीमेटली आपने इसको कन्वर्ट करना है रो और सिग्मा में। ठीक है। मैं अब आप सोचेंगे इसको कैसे, जो है ना वो आप, और जो दूसरा डी है उसको भी लिख लें। दो डी है ना आपके पास। एक ये डी है और एक ये डी है, दोनों को लिखें। या आपके सामने कुछ आइडेंटिटीज भी लिखी हुई हैं, इनकी मदद से ट्राई टू हैव अ सिमिलर एक्सप्रेशन जिनसे कंपेयर करके यू कैन कम अप विद दिस इनइक्वालिटी। उसके ऊपर सिर्फ एक ही चीज आपको चाहिए, मैं लिख देता हूँ। अच्छा चलें, बोर्ड और नीचे करना है। इससे नीचे तो होगा नहीं अब। अच्छा चलें, आई थिंक दिस इज प्रॉब्ली लिटिल बिट आप के लिए मुश्किल है, सो लेट मी। जी जी, पता नहीं आपके क्वेश्चन का क्या मतलब है। ये तो आप प्रूव ही तो कर रहे हैं ना, अब अभी जो बात आप कर रहे हैं यही कर रहे हैं ना आप। देखिए मैथमेटिक्स क्या है, बस आर्गुमेंट्स को थोड़ी वो एक सॉलिड फॉर्म ही देते हैं ना, और क्या है। को मैथमेटिक्स ये तो नहीं है कि कोई इलॉजिकल चीज है। तो बस जब आर्गुमेंट, जैसे अभी आपने बात शुरू की है, तो ये आप प्रूव ही करने की कोशिश कर रहे हैं ना। आप एक्सप्लेन करें लॉजिकली ऐसे ऐसे, बस जब आपकी आर्गुमेंट्स के वो जो पार्ट्स में थोड़े ज्यादा हो जाते हैं, वी स्टार्ट इंट्रोड्यूसिंग सिंबल के, इस पार्ट को मैं ये कह दूं देन दिस इज, थोड़ा थोड़ा वो एक लॉजिकल स्ट्रक्चर आ जाता है। सो लेट मी ट्राई टू शो इट। जो लेट्स स्टार्ट विद दिस वन। तो पहले तो ये देखें, अगर रो माइनस सिग्मा जो है हमें पता है दिस इज इक्वल टू क्यू माइनस एस, तो इससे एक चीज तो मेरे पास आ जाएगी क्विकली कि ट्रेस ऑफ रो माइनस सिग्मा इज इक्वल टू ट्रेस ऑफ क्यू माइनस एस। दिस इज जीरो राइट, ये हमने लास्ट टाइम भी देखा था, क्योंकि रो और सिग्मा का ट्रेस वन वन होता है, तो वन माइनस वन इज जीरो। तो इसका मतलब है कि ट्रेस क्यू इज इक्वल टू ट्रेस एस, एक आइडेंटिटी तो ये आ गई। दूसरा अगर आप देखें तो आई कैन चेक अनदर थिंग कि अगर लेट्स से all of this and this pass through a channel, so rho minus sigma and q minus s passing through a quantum channel, and since this is a linear operation, this means this minus this minus this। अब अगर मैं इसका ट्रेस लूं हर तरफ, तो ये आ जाएगा ट्रेस ऑफ this minus trace of this, ये आ गया। और ये चूंकि ट्रेस प्रिजर्विंग है, तो अगेन इसका ट्रेस रो के ट्रेस के बराबर, इसका ट्रेस सिग्मा, तो दिस इज अगेन जीरो। ठीक है, या जीरो से आप यू कैन फाइंड आउट द ट्रेस ऑफ ई क्यू इज इक्वल टू ट्रेस ऑफ ई एस, लेकिन मैं इससे भी एक इसकी बजाय एक और आइडेंटिटी भी हासिल कर सकता हूँ, ट्रेस ऑफ ई ऑफ रो माइनस ट्रेस ऑफ ई ऑफ सिग्मा, दिस इज इक्वल टू ट्रेस ऑफ ई ऑफ क्यू माइनस ट्रेस ऑफ ई ऑफ एस। सो इन चीजों को लेके लेट्स नो स्टार्ट विद द लेफ्ट साइड। तो जो लेफ्ट साइड का ये है ट्रेस डिस्टेंस बिटवीन ई ऑफ रो and E of sigma, this is equal to trace of P E of rho minus E of sigma, right? Over where this P is some projector which maximizes this thing. So this is equal to this, and G, हाँ मैंने कह दिया बोल दिया कि P is some projector that maximizes it. और अगर मैं इस राइट साइड को देखूं तो व्हाट इज दिस D is rho sigma equal to something half trace rho minus sigma, and this is equal to half trace Q minus S, और इसका हमें ये भी पता है कि दिस इज इक्वल टू हाफ ट्रेस Q प्लस S, और चूंकि Q और S का ट्रेस बराबर है तो मैं इसको यूं भी लिख सकता हूँ 2 टाइम्स ट्रेस ऑफ Q, तो दिस इज जस्ट ट्रेस ऑफ Q. सो जो ये डिस्टेंस है ये ट्रेस ऑफ Q के बराबर आ गया. एंड यहां से हमने ये भी देखा है कि because this is equal to 0, so it means that this is equal to this trace of Q minus S. So yahan se we can see that trace of Q plus S, this one, this is equal to, yeah, okay, yahan se directly we can say trace of, this is equal to trace of E of Q. Can we see this? Because this is the main step. Let's see from here. Okay, this is equal to this. Trace of E of हाँ ठीक है, मैं देखें दिस इज एग्जैक्टली ट्रू, क्योंकि Q जो है एक पॉजिटिव ऑपरेटर है. When it passes through a channel, since it's a trace preserving channel, इसका ट्रेस और इसका ट्रेस बराबर होना चाहिए. Okay, so and this is equal or greater to trace of some projector times E of Q. देखें अब this is something, so ये कोई ऑपरेटर है E of Q. अब मैंने इसके साथ एक प्रोजेक्टर लगा दिया. So in general this thing is always going to be smaller than this thing. क्यों? क्योंकि प्रोजेक्टर जो है it will project this thing into a subspace, and क्योंकि this is a positive operator, this is always going to be smaller than that. So this quantity is always smaller than this thing, and this thing is even smaller than trace of P E of Q minus E of S. क्यों? क्योंकि मैंने इस पॉजिटिव ऑपरेटर से ये कुछ जो है ना वो माइनस कर दिया. एंड दिस इज नथिंग बट दिस डिस्टेंस, सो दिस इज इक्वल टू D of E of rho minus comma E of sigma. तो हम देख रहे हैं कि ये जो डिस्टेंस है E of rho और E of sigma का, this is smaller than this distance, and that's what we wanted to prove. That in general, any trace preserving channel, which is, this is the main link, that trace of Q is equal to trace of E of Q. If this is true, then we can see that this distance is smaller than that distance. And this is actually an extremely important theorem, and it has consequences for quantum computers as well. क्योंकि quantum computer जो है वो क्या करते हैं, let's say number one, that you have some circuit and you have some output. So usually you have some input and some output, and generally the output is a function of the input. और अगर तो ये आपका noiseless quantum computer है, it doesn't add any noise, so then this is a unitary operator. So a quantum computer is a unitary operator. कि अगर यहाँ पे आप कोई स्टेट रो देते हैं, सो वी गो टू यू रो यू डैगर, अगर कोई स्टेट सिग्मा देते हैं वी गो टू यो सिग्मा, एंड वी हैव ऑलरेडी सीन कि यूनिटरी ऑपरेटर डजंट चेंज द डिस्टेंस. अगर यहाँ पे दो डिस्टिंक्ट स्टेट्स हैं, you will have two distinct outputs. But if this is a noisy quantum computer, which all quantum computers are, and almost, I mean, most likely they are always going to be noisy. I mean, we can reduce noise. So then this is essentially a quantum channel. और हमने देखा है कि in general जो quantum channel है वो ये क्या कर रहा है? You start with different states and you end up with two states, rho prime and sigma prime, which are closer. और अगर ये जितना वर्स क्वांटम कंप्यूटर होगा दे विल बी इवन क्लोजर. सो और अगर ये बहुत ज्यादा खराब क्वांटम कंप्यूटर है, विच यू नो मोस्ट ऑफ द क्वांटम कंप्यूटर टुडे आर, सो व्हाट इज हैपनिंग कि आप यहाँ पे जो मर्जी डिफरेंट इनपुट ले लें, यू स्टार्ट विद 000 और यू स्टार्ट विद 111 और सम 010, यू माइट एंड अप विद एग्जैक्टली द सेम आउटपुट. कि जिस मर्जी स्टेट से शुरू करते हैं, प्रोजेक्ट्स यू ऑन द सेम स्टेट. कि अब जो डिस्टिंक्ट स्टेट्स हैं दे आर बीइंग प्रोजेक्टेड टू द सेम स्टेट, यानी उनका डिफरेंस कम होता जा रहा है. So essentially you are ending up very close to each other. So this theorem says that in general if you have noise you are always going to end up closer. Number 2 जो है एक और भी इसकी आप समझे कि कॉन्सिक्वेंसेस हैं, और वो ये है कि आप को याद होगा कि हमने ये शुरू में डिस्कस किया था कि if we think of our system as coupled to environment, so what we can do, we can think of a state which is let's say a pure state formed by the system and you know some reference system or some reference environment, and then by tracing out the environment or something else we can get the density operator of the system. Let me show it a little bit rigorously. So let's say we have some system A and some system B, and let's say there is some pure state rho psi AB, or even if not pure, let's say there is some density operator AB which represents the joint state of A and B. And if we trace out you know, let's say system B, we can get the state of system A. Similarly, if let's say we have another state sigma AB of two systems and we trace out system B, we get a state of system A. अब ये दोनों जो operations हैं, they are trace preserving maps, and but from that theorem we see that even if these two states are far apart, these states are going to be closer than rho AB and sigma AB. That even if the state of two joint systems are apart, the states of a single system in general are going to be closer. That if you know trace out part of the system, what you will end up with states which are going to be closer. And there's actually sort of a nice analogy जो book में बयान की हुई है. Let me try to show it here. That might help you remember. Suppose you know you have these two emojis, and you know this is rho AB, this is sigma AB, and they look different. But suppose I trace out part of the system and you're not able to see, you'll see that they're almost the same. अगर मैं थोड़ी जरा सही फिगर बनाने में कामयाब हो जाता तो it would exactly have been the same. So this is in general, okay? There is an equality and that thing. So it's not going to be always true. You're absolutely right कि अगर ऊपर से कर दें, they will still look different. But the but they're not going to be further apart than this. This is not going to be like this. This is not allowed. At best, this is what can happen, that the distance is going to remain same according to that theorem, that the channel can only reduce the distance between states. It cannot increase the distance. Okay. Acha, we can continue discussion of properties of trace distance. Ji. यहाँ पे तो इस तरह का कुछ नहीं हो रहा. हमने तो ऐसे तो कुछ नहीं कहा कि डाइवर्ज कर रही है कुछ चीजें. Okay. Okay, so there are a couple of other properties जैसे convexity है, strong convexity, joint convexity, and I'll give one of them in the homework so you can see it there, but not going to spend too much time on this. Ji. वो किस स्टेट में थी? ऐसा कोई चैनल नहीं है. हमने डिस्कस भी किया था when we were discussing channel that you can always reduce purity, you cannot increase it. Okay. There is possibility of increasing purity, by the way, but that is if you couple your system with an environment such that environment has a memory. Initially, let's say due to some reason, if your channel has lost some information, and the environment can store it, and then later on it can restore the information back into the system, and your purity can increase. These types of channels are non-Markovian channels. But that's not going to be a trace preserving channel. Okay, so अगर आप वो मुश्किल थ्योरम प्रूव नहीं कर सके, so what I would like you to do then, prove this triangular inequality for this trace distance. So suppose you have trace distance between two states, rho and tau, and then sigma is some other state. Show that the sum of this distance is always greater than this distance. You have like 5 minutes. जी? Sorry? मुझे नहीं समझ आ रही है. हाँ हाँ, सारे जो क्लास प्रॉब्लम्स है यू कैन डिस्कस. Excuse me. अफसर ये वाला प्रूफ करना, ट्रायंगुलर इनइक्वालिटी. again, as a starting point, you know, this type of description will be helpful. Instead of, you know, writing the distance as half trace mod of difference of states, usko trace of projector time difference वहां से शुरू करें. हो गया? चलिए फिजान कलेक्ट कर. ये सिंपल एक स्टेप में हो जाता है. इन लोगों को आपके इतना टाइम कैसे लगा? सो जैसे ये D है, I can write it like this: trace of some projector P that maximizes this quantity, right? I can write it like this. So this P is a projector that maximizes this quantity. And then I can easily this rho minus tau के अंदर, let's say I subtract a sigma and I add a sigma. Okay, and then क्योंकि trace linear है, you can write it like this. Sigma minus tau इस तरह से कर देते. ओके, अब जो पॉइंट याद रखने को है वो ये कि ये P वो था जो इसको मैक्सिमाइज करता है, और जरूरी नहीं कि वो इसको मैक्सिमाइज करे या इसको करे. सो इन जनरल दिस इज लेस देन और इक्वल टू द ट्रेस डिस्टेंस rho sigma distance of sigma tau. ठीक है सभी? तो ओके जी, राइट साइड से कर लें. देन उसका तरीका ही होगा कि इसको आप लिखेंगे, लेट्स अटेम्प्ट फ्रॉम द राइट साइड. तो जो d rho sigma है और d sigma tau, this is equal to trace some projector P1 which maximizes this one, some projector P2 which maximizes this one, and this is equal to some trace of इनको collect कर लें, and then you'll have to argue that why this is greater than something this, but it's quite easier from the left side. Okay, so that's all that I have to say about the trace distance for now. It's actually very important in quantum information processing. A lot of time it's used. And then there's another measure of distance, which is fidelity, which somehow is becoming more popular, especially in quantum computation side of the quantum information literature. And we'll spend quite some time on this thing. So this quantum fidelity is the generalization of the classical fidelity, and it's defined in a very frightening way like this: trace of square root of rho power half sigma rho power half. So this is the definition of this one. Initially it doesn't look intuitive, look little bit hard, but hopefully when we start working with it, it becomes a little bit easier for you. And you always have to remember these rho sigma, these are operators, these are density operators representing the states. Right now it doesn't even look symmetric in rho and sigma, but we'll see soon that this indeed is symmetric in rho and sigma. Okay, so let's start with few examples so that you start to get some feeling of this definition, and then we'll study its properties and some theorems that we will be able to define it some other ways, and just like we did it for the trace distance. And we'll also discuss alpha, which is sort of a metric, because this itself is not a metric. We can't prove this triangular inequality like that for this thing. Okay, so example number 1, let's start with states that commute, which means that I can write rho as in a diagonal form in, let's say, a certain basis with the eigenvalues Ri, and I can diagonalize sigma as well in the same basis. So if rho and sigma are this, let's try to compute this fidelity. So uske liye first I need rho square root. So rho square root would be Ri square I. Okay, because this is diagonal, and for diagonal matrices, if we have to apply any function on the operator, we just need to apply it on the diagonal. या इसको आप उल्टा भी अगर आप थोड़ा सा काउंटर इंट्यूटिव लग रहा है तो ये समझ लें कि इस रो स्क्वायर रूट को अगर मैं इसके अपने आप से मल्टीप्लाई करूं, वी कैन सी दैट वी गेट दिस. Okay, you can just quickly check. Row half into row half would be I Ri square root I times, let's say, J Rj square root J, and sum over I and J Ri Rj square root I J. Now this is I inner product with J, and since these are same basis state, so there are orthonormal. So this inner product would be delta Ij, which is non-zero only when I is equal to J. So sum over J goes away, and this I has to be equal to J for non-zero entries. So this becomes Ri square, square goes with square root, so I get Ri I. Okay, so this indeed is square root of this operator. So let's now try to evaluate fidelity of these states that commute. So trace square root of I Ri square root. For sigma, it's J Sj J. अच्छा, इनिशियली काफी लोग ये गलती करते हैं कि व्हेन वो इस तरह के जो सम्स हैं सब्स्टिट्यूट कर रहे हैं कहीं पे, तो यहाँ पे बेशक वो इंडेक्स सेम ही लिखे हुए हैं, दे स्टार्ट पुटिंग things with the same index. It's not right. Okay, when you, because this is a sum, this is a sum, this is just a dummy index. तो यहाँ पे लाएंगे तो in general the indices are different. So be careful. हो सकता है बाद में किसी प्रोडक्ट की डेल्टा की वजह से सेम हो जाए, बट इन जनरल, so this is, let's say, k r k k k. Okay, so fortunately क्योंकि ये सारे जो हैं वो सेम बेसिस है, जब इसको इससे मल्टीप्लाई करेंगे तो ये j और k उसी वक्त नॉन जीरो होंगे व्हेन j इज इक्वल टू k. सो ये इंडेक्स भी सेम हो जाएगा, और इसी तरह ये जो j और i है ये भी उसी वक्त नॉन जीरो होंगे जब व्हेन i इज इक्वल टू j. सो ऑल दीज थ्री प्रोडक्ट्स sums reduced to the single sum, and this becomes ri si. Okay, अब ये भी डायगोनल मैट्रिक्स है, तो इसका जो स्क्वायर रूट है वो इसका स्क्वायर रूट सिर्फ हो जाएगा. नाउ ये जो ट्रेस है, I can get this trace in here. This is trace 1, so Ri, which is the classical fidelity between two probability distributions with elements are probabilities Ri and Si. So just like the trace distance, जब states commute करती हैं, तो we saw that the quantum fidelity is the same as the classical fidelity. Okay, but this is just a special case. In general, you know, this will not be equal to that. हमने वहां पे भी देखा है कि in general जो classical trace distance था, it wasn't equal to the quantum trace distance, but the quantum trace distance was an upper bound for this classical trace distance between the probability distribution of some measurement operators. But when the states do commute, then वहां पे भी वही बराबर हो गया था और यहाँ पे भी it's the same thing. Let's take another example, and this is actually one of the important example because this is a case which is quite common. So example number 2, suppose we have a pure state and a mixed state, और उसकी हम fidelity find करना चाहते हैं. And for that purpose, let's say our state, rho is this, and we have other state is sigma. Okay, so ये कोई mixed state है, लेकिन जो raw state है, suppose it's a pure state, which means that I can write it as psi. अब इस केस में जो fidelity है, उसके लिए पहले तो मैं इसका rho का square root find करूंगा. सविता बता सकती हैं rho का square root क्या होगा? कोई गेस कर लो. हाँ, ये रो प्योर स्टेट, लेकिन ये इसका डेंसिटी मैट्रिक्स मैंने लिखा हुआ है सामने, ऑलरेडी डायगोनल है जी. √1 आ जाएगा, तो √1 तो 1 ही होता है ना, यही आ जाएगा. दूसरा तरीका ये देखने का ये है कि अब ये जैसे ये स्क्वायर, इसको मैं इसी से मल्टीप्लाई करूं तो क्या मिलेगा, यही मिल जाएगा फिर. अब टेस्ट कर लें, ठीक है. इसको मैं इससे कर दो तो ये तो 1 हो गया ना, तो अगेन साई. दूसरा तरीका ये है कि दिस इज अ वेरी सिंपल डायगोनल मैट्रिक्स, ये सिर्फ 1 है, ठीक है. एक ही 1/1 मैट्रिक्स है और उसका डायगोनल एलिमेंट 1 है, इसका स्क्वायर रूट 1 का भी 1 ही आ गया. ओके, ऑलराइट. सो ये इसलिए कहते हैं कि बबल नहीं खाते, उससे जो दिमाग है ना वो काम करना छोड़ देते हैं. रो स्क्वायर रूट सिग्मा रो स्क्वायर रूट, क्योंकि एट ए टाइम हमारा ब्रेन कहते हैं सिर्फ एक ही काम कर सकता है. रियली स्पीकिंग दिस इज, वो जो कहते हैं कि खाना खाते वक्त बातें नहीं करनी चाहिए, या बल्कि सोचना भी नहीं चाहिए. बात का बंदा सोचो में गुम होता है, खाना खाते खाते गोता लग जाता है. All the neurons they are mixed up, in something else. Anyway, so this is this, so this becomes ये चीज आ गई. अब जो है वो हमने इसका स्क्वायर रूट और ट्रेस फाइंड करना है. ओके, सो let's do it here. अच्छा, इसमें देखें कि ये जो चीज है दिस इज जस्ट अ नंबर, राइट. सिग्मा psi sigma psi, this is just a number. Okay, this is the expectation value of this operator sigma. So ये नंबर जो है ये स्क्वायर रूट से आप बाहर इधर निकालें या इवन यहाँ पे बाहर भी निकाल सकते हैं. So let me just take it out. Psi sigma psi square root trace this. अब इसका ट्रेस फाइंड करने से पहले वी हैव टू फाइंड इट्स स्क्वायर रूट. वो तो हमने पहले देख लिया कि इसका स्क्वायर रूट भी ये इटसेल्फ ही है. सो दिस बिकम्स और फिर इसका ट्रेस भी 1 होगा. ओके, बिकॉज ट्रेस ऑफ दिस थिंग इज दिस. सो अगर ये नॉर्मलाइज स्टेट है, दिस इज जस्ट 1. सो दिस इज द फिडेलिटी बिटवीन a pure state and a mixed state. And you can see this is just an overlap between your pure state, the square root of the overlap between between your uh, between the pure state and whatever the mixed state is. And just as a special case, suppose this sigma itself is some pure state. So suppose sigma represents some pure state itself, then this fidelity between two pure state would just be psi, phi, phi, psi, and this is the conjugate of one another. So this becomes psi, phi, mod square, square root, and this is just psi and phi. हाँ, सिग्मा डेंसिटी ऑपरेटर में कुछ भी हो सकता है. ओके, सो यहां तक ये मिक्स्ड ही थी, but now I just wrote what the fidelity would be for two pure states, and it's just the inner product between the two pure states. And you see now it sort of makes sense why that particular definition, क्योंकि हमारा यूजुअली हमने अगर देखना हो दो क्वांटम स्टेट्स हैं प्योर स्टेट्स के वो कितनी सिमिलर हैं, तो ऑल वी हैव to do is just find the inner product. Again, inner product 0, it means they are orthogonal. They are, as different from each other as they possibly could be. And if the inner product is 1, they are the same state. अच्छा, अब ये जो fidelity है ना between a pure state and the mixed state, this is actually a very common occurrence because it's used in many ways. Let me give you a couple of things that this is becoming popular in literature. फर्स्ट करें आप एक क्वांटम कंप्यूटर डिजाइन जी, ये वाला ये कि if the other state is also pure state, तो फिर सिग्मा क्या होगा, सिग्मा होगा फाई फाई, राइट. तो अब मैं इन्हें इसको यहाँ पे सब्स्टिट्यूट किया, तो ये आ गया साई ये वाला, और फिर ये सिग्मा की जगह पे फाई फाई और साई, और ये देखें ये साई फाई का नर प्रोडक्ट है और ये फाई साई ये एक दूसरे का कॉन्जुगेट होते हैं ना, तो इसका मतलब है दिस इज मॉड स्क्वायर ऑफ साई फाई, तो ये स्क्वायर स्क्वायर रूट से कैंसिल हो गया, आई गेट दिस मॉडुलस ऑफ फाई साई. ओके ओके, सो एनीबॉडी एल्स अबाउट दिस एग्जांपल. अच्छा, मैं इसका यूज जो है ना वो थोड़ा सा बताने लगा था कि व्हाई इट्स सो यूजफुल. सो सपोज one thing is that you are, let's say you're trying to design a quantum computer. So quantum computer essentially has two basic things, like if you forget about the measurement and everything else, जो basic चीज आपको चाहिए, that you have a qubit and you need to be able to perform some unitary operations on it. Okay, suppose you want to be able to perform some gates on it, so let's say x gate, z gate, या अगर multiple qubit हैं, control x gates, etc. So it means that if I want to perform the x gate, my 0 should go to 1 and my 1 should go to 0. Yeah, I can come up with some this state, this should go to alpha 1 plus beta 0, right? But what happens जब आप इसको हार्डवेयर में इंप्लीमेंट करते हैं, तो it's a noisy hardware. It's not an ideal unitary operation. It's essentially a quantum channel. So your pure state goes to a mixed state. So one way of quantifying how good your hardware is, how good your gate is this fidelity. That what people do, okay, that the fidelity is then computed between what you should get, this psi prime, and what you actually get when you perform this gate in the hardware. So with this, agar तो आप हार्डवेयर में let's say implement करते हैं and this state goes to this as it is, then your fidelity is 1. But if this is a mixed state, in general this fidelity would be less than 1. And that's, nowadays, right now, perhaps one of the most commonly used metric to quantify different hardware के जी IBM के जो gates हैं उनकी कितनी fidelity है, Google कितनी है, या दूसरे बहुत सारे लोग, या maybe you are making a gates in your lab, so what's the fidelity of gate? That's the common term, and that's where this is used, that what you should get pure state and what you actually get, उनका जो overlap है, that's how the fidelity is measured. And just to give you an idea, um, right now people have been able to get to gates with fidelity as high as 10 power minus 4 or even 10 power minus 5, 1 minus. So very good fidelities for at single qubit gates. जो multi qubit gates हैं, let's say control X, unfortunately the fidelities for these control X gates, they are usually in the range of 10 power minus 2 right now, and usually it's even worse than that, because when you have multiple qubit, then आप बेशक let's say आपके हार्डवेयर पे 10 qubits हैं, तो अगर आप 2 gates में, तो वो noise दूसरी वजह से भी आ रहा होता है, but this is the best that people have been able to, like 0.99. Okay, and this is not just to quantify this thing. Also, if you want to measure the quality of your qubit, for example, you don't do anything, you just do identity operation, then your state 0 should remain 0 and 1 should remain 1. But even if you don't do anything, because of noise and everything else, your 0 starts to go into a mixed state. Okay, let's say it's a depolarizing channel. So your 0 state begins to go to some rho plus some half with some, let's say, probability p and some probability. It's going towards this class, it's maximally mixed state. So you can quantify the quality of your qubit also with fidelity, that what state you should be and what you actually go to after a certain time. जी सॉरी, दोबारा पूछिए. हाँ, तो वो लिखा सब, वो सबसे ऊपर उन्हीं ने लिखा हुआ, रो और सिग्मा. नहीं, वो तो एक एग्जांपल ही है ना, वो तो, और रो सिग्मा दोनों डेंसिटी ऑपरेटर्स हैं, वो कुछ भी हो सकते हैं. ओके, सो जो डेफिनेशन दी है वो तो जनरल डेफिनेशन है, इट्स फॉर एनी टू मिक्स स्टेट्स. तो ये तो एक एग्जांपल मैंने ली, एक एग्जांपल वो ली थी जब रो और सिग्मा दोनों मिक्स स्टेट्स हैं बट दे कम्यूट. ओके, so it means that they can be diagonalized in the same basis. So RISIs, they are probabilities with which you have mixed those states to get that state. For example, let's say one thing is this ke aap 0 और 1 state को इस तरह से mix करते हैं. Let's say your sigma is maximally mixed state. So you can find the fidelity using this formula. Actually ये classical fidelity से ही आ जाएगा अगर आप इनको as a probability treat कर लें. क्योंकि हमने देखा है कि when they, क्योंकि दोनों ये commute करती हैं, इसलिए ये दोनों एक ही basis में diagonal है. Okay, so जो expression है, it's the general one. हाँ, okay, आपको गेट वाली बात समझ में आ गई है? तो जो क्यूबिट वाली बात है वो उससे भी सिंपल है कि लेट्स से यू जस्ट डू नथिंग and then you measure your state, and let's say that state is sigma, but you know that if you don't do anything, आपकी state होनी तो वही चाहिए जो शुरू में थी. So you compute fidelity between the state that was initially there and what you actually get after some time. Okay, so that can tell you the quality of your qubit. Okay, all right. Okay, so जी.
प्रोडक्ट डिफाइन किया था दो मैट्रिसेस का,
हम्म,
मुझे लगा था कि हम आई नो कि नजर आ रहा है कि ये मतलब जब कंप्यूट करें दो वेक्टर्स को ये ब्रेक डाउन करें क्लासिकल, वो भी नहीं यूज कर पाते।
तो आप असल में एक और जो है वो डिस्टेंस मेजर उसकी बात कर रहे हैं, यू नॉट टॉकिंग अबाउट फिडेलिटी।
उससे भी वैसे ये हो जाता है।
नहीं, वो तो इससे डिफरेंट चीज होगी, आप ज़ाहिर उसको डिफाइन ही डिफरेंटली कर रहे हैं। यू आर सेइंग के इट्स रो डैगर सम सिग्मा, ठीक है। तो पहली बात तो ये है कि एट द आउटसेट यू आर गोइंग फॉर अ मीट्रिक विच इज नॉट सिमेट्रिक, ठीक है। एंड देन जो भी है आप फिर आप उसकी प्रॉपर्टीज यू कैन वर्क आउट के उसका क्या फायदा है डिफरेंट सिचुएशन में, वो हेल्पफुल हो सकती है कि नहीं हो सकती, बट दैट्स अ पॉसिबिलिटी। मैंने जैसे शुरू में कहा कि देयर, so you want to compare two probability distributions essentially, and there are almost like as many variables as the number of elements in the index set. You can come up with uh, uh, like exponentially many ways of comparing those numbers in two different sets. Okay, all right, so I'm going to stop here, but let me just give one statement. It's called Ullmann theorem, जो कि हम next class में prove करेंगे. It's one of the most important theorem concerning fidelity, and we will show that कि जो fidelity है, we can prove it, we can define it in an alternative way. कि हमें पता है कि कोई भी जो किसी सिस्टम की मिक्स स्टेट है, हम उस मिक्स स्टेट को रिप्रेजेंट कर सकते हैं एज अ प्योर स्टेट of that system combined with another system with a reference system, right, such that कि वो जो combined state है उसमें से वो अगर reference को हम trace out करें तो we get this mixed state back. Remember this thing? So it means कि अगर आपके पास दो states हैं rho और sigma, so I can purify, this is called purification, I can purify rho to let's say some state psi, and I can purify sigma to some state let's say phi, and then I just compute inner product between rho and psi. And then this fidelity can be shown to be the maximization of that inner product. Okay, you purify it in such a way that that inner product is maximized. We'll prove it, rigorously in the next class. So you have like 30-minute break before the seminar. तो आज फिर हम यहीं पे स्टॉप करते हैं, बट ऑन मंडे we'll have two classes on Tuesday. अच्छा, आपके नेक्स्ट थर्सडे को आपका मिड टर्म है, तो आई सेंड आउट होमवर्क टुडे जो कि एसेंशियली प्रैक्टिस प्रॉब्लम्स होंगे, आपको मिड टर्म में हेल्प करेंगे, एंड यू हैव टू सबमिट इट बिफोर द मिड टर्म. नहीं, ट्यूसडे वाले भी होंगे. हाँ, तो ट्यूसडे को आई जस्ट डू मेनी मोर एग्जांपल्स फॉर फिडेलिटी, दैट्स ऑल आई एम गोइंग टू डू. तो आप यू विल गेट कंफर्टेबल विद दिस थिंग. वो है थर्सडे को. थर्सडे को अब हमने क्लास भी लेनी है, प्लान तो ये है. तो विल सी के कोई पहले मिड टर्म लेते हैं या पहले क्लास.